Hello, my name is Chase Henderson. Today I'd like to talk about the current state of coronavirus testing in Oregon. In this presentation, we'll move through Goal 1. We'll review the data source, discuss positive percentage, and explore the data. This will set us up to segue into Goal 2 and 3 later on, which will have more to do with model development and refinement in later presentations. Our data is imported from the COVID tracking project at covidtracking.com. The COVID tracking project is a volunteer organization launched by the Atlantic focused on COVID-19 combative efforts. This particular data, the Oregon data set is given an A+ grade for data completeness. This analysis will be primarily focused on positive percentage. Positive percentage is calculated by taking the positive test cases and dividing it by the total test results. Here are some of the exploratory data analysis statistics of that feature. In particular, what you can notice is that initially the national averages have more observations than the total N of Oregon, meaning that the date that Oregon's statistics started up was a later point in time. So in order to line up all of our statistics correctly, we've started at the beginning of when Oregon started these statistics on March 3rd, 2020. While running totals like total positive coronavirus cases or total tests can be overwhelming and not very helpful for comparison and benchmark purposes, the positive percentage statistic tool gives us a clean comparison tool. Current coronavirus management guidance seeks to keep positive percentage rate below 15%. Oregon has not only done a fairly effective job staying below that percentage, it also as a state has performed well below the national average. Moving into our Oregon exploratory data analysis, we'll see time realizations displaying wandering trend behavior. Spectral density peaked at 0, and a slow dampening effect in the sample autocorrelations, which will always happen in part because of how the sample autocorrelations are calculated. But we can also say this data we may assume that this data is non-stationary. The good news is the slowly dampening autocorrelations may also be a good indication that we have potentially a strong ARIMA model here. Similarly to the Oregon data, the exploratory data analysis, the national statistics also display wandering trend behavior, slowly dampening sample correlations, and spectral density peak at 0. To transform the non-stationary data to stationary, the Box-Jenkins approach was used. A high pass filter was applied, and the first difference effectively transformed the data. The same filter was applied to the national data and also was effectively transformed. With the goal of starting from a simpler model approach, a BIC was used to guide the P and Q estimates, and an AR4 model was considered promising and is reflected in this equation. This baseline ASE will be used in comparison with all the subsequent model forecasts. The same Box-Jenkins approach was applied to the national data. After a BIC analysis was done, an ARIMA 1.1 was considered the best model for our starting point. This model, when used with the applied P and Q, resulted in this simple model ASE of 4.169. The next steps. With this data explored and the initial baseline models created, we can move into Goal 2, building a new univariate fit, and then into Goal 3, as we complicate the model even further with multivariate fits and var fits. So for now, that concludes my presentation. As we work to bring in new features and new approaches and new parameters, this model should be improved even further moving forward. Thank you very much for your time. Look forward to speaking with you all again.